All right, good afternoon and welcome back. This is our first lesson on verifying trigonometric identities. And as I've written on the board here ahead of time, you can see that there are three takeaways from this branch of trigonometry, and we're going to spend several lessons on this topic. Today I'm going to start very simple, but number one is definitely the most important thing that you're going to gain from this, and that it's going to improve your algebra problem-solving techniques, meaning that your ability to add and subtract fractions, your factoring skills, your simplification skills, all the techniques that you learned in the middle part of Algebra 1 and Algebra 2 are going to be not only tested at this point, but they're going to be strengthened as well. And so you're going to understand these things a lot better. Secondly, it will also provide you a richer understanding of the relationships between trigonometric functions. What do I mean? How do sine, cosine, and tangent relate to one another? And lastly, I guess this is also almost as important as number one. It's probably more important if you were to continue on in college level math classes, and that it's going to introduce proof techniques necessary for success in those classes. And what do I mean? I guess primarily, or at least my hope is that every single one of you that watches this will at least gain a familiarity with the structure of proof, meaning the left to right format that we're going to use to prove these things. Okay, there's something missing from the whiteboard that I'm going to have to address near the end, but let's go ahead and get started. These are the geometric definitions. Obviously, you guys learned this in class. The sine of an angle theta. Notice theta has been listed in this right triangle as the opposite divided by the hypotenuse, which is A over C. Cosine is adjacent over hypotenuse, B over C, and tangent is the opposite divided by the adjacent, A over B, and then you have your algebraic definitions if we're working on an XY axis. But we're going to start with proving that the tangent of theta is equal to the sine of theta over the cosine of theta. And when you prove these identities, most of the time it's easier. And there's no one right way to do these necessarily, but the hint that I can give you is most of the time it's easier to start with the most complicated side and work toward the simpler side. So in this case, if you were to ask looking at this equation, which side looks more complicated, you would probably say the right side. And so we're going to consider this to be the more complicated side. We're going to start with the sine of theta. To actually prove this, we're going to write our proof right here. We're going to start with the sine of theta over the cosine of theta, and we're going to go back to the definitions of the sine of theta and the cosine of theta given this right triangle. Notice that if an angle theta has been labeled in a right triangle, we know that the sine of theta is A divided by C, and that would be the opposite divided by the hypotenuse. So we can replace the sine of theta with A over C, and we know that the cosine of theta is B over C in this triangle, or the adjacent over the hypotenuse. So we have B over C, and this is going to equal, notice that we have a fraction divided by a fraction, and in this case we're going to take the top fraction, A over C, and multiply by its reciprocal. So this division problem is equal to the multiplication of the reciprocal of the bottom. So you take the top fraction, A over C, multiply by C over B. So notice that we flipped the bottom fraction, B over C, and made it C over B. And notice that when there's multiplication, we are allowed to cancel the C's, and our final answer here after this is going to give us A over B. And if you notice on this triangle, what is A over B? Notice that A over B are the opposite divided by the adjacent, which is the definition of the tangent of theta. And so now we have that this is equal to, we generally go left to right, but I'm running out of space. So we're going to say that this is equal to, if you guys have to go to the next line, you put the equality in front of the statement on the second line. So in this case, it's going to equal the tangent of theta. And notice we've shown that the first part is that the sine of theta over the cosine of theta is equal to the tangent of theta through a string of equality. Notice that sine of theta over cosine of theta is equal to this, which is equal to this, which is equal to this, which is equal to the tangent of theta. And so therefore we have proven, using the definitions that we already know, that these two things are equal. And notice we did not write the entire equation, we just wrote one side of the equation to start. Now, on the next proof, you can do this similarly. You can start with the most complicated side, which is the cosine of theta over the sine of theta. We're going to start with cosine theta over the sine of theta. And the good news is that all of the proofs that you're asked to do in trigonometry are already true. So you're not trying to show whether something is true or false, but the hint is that everything that you're asked to prove on the board is already true. And so you just have to show that the left side is equal to the right side through a string of equalities. So in this case, we're going to start with the cosine of theta over the sine of theta, and we're going to do it the same way. Notice that the cosine of the angle theta is defined to be what? B over C. And the sine of theta is A over C. And the same thing here. We take the top fraction, which is B over C, and we multiply by the reciprocal of the bottom fraction, which is C over A. And I know that you guys did this in class before school was out, so you guys are already familiar with this. Notice that we get B over A, and notice that B over A would be the reciprocal of the tangent of theta, and this brings me to the part where I said I did not write this on the board, but we know there's a second, I'm going to have to erase very quickly, there's a second part, there's a second set of, we also have what's called the reciprocal definition, so I'm just going to go ahead and put it right here. That the cosecant of theta is equal to 1 divided by the sine of theta, and the secant of theta is equal to 1 divided by the cosine of theta, and the cotangent of theta is equal to 1 divided by the tangent of theta. And notice that B over A can be written as 1 over A over B. And notice that if I look at this as going this direction, if I were to, sometimes it's hard to see this is kind of a complicated step, but if I started with 1 over A over B, do you guys agree that that would be 1 multiplied by the reciprocal B over A, which is equal to B over A? So I'm showing you that B over A can be written as 1 over A over B, and notice that A over B is the tangent of theta, so we now end up with 1 over the tangent of theta, and 1 divided by the tangent of theta, notice, is defined to be what? The cotangent of theta. And as we go forward, you guys are going to learn to skip steps. You guys are going to learn that, okay, cotangent is nothing more than the reciprocal of the tangent function, so if I have B over A, that would be the reciprocal, and it would be acceptable to just stop your proof right here, that we understand when the tangent, when the opposite and the adjacent are flipped, or we have the reciprocal relationship, that that's just the same thing as the cotangent of theta. So I would be fine with this. Now, we also talked about the Pythagorean identities before you left. That the sine squared of theta plus the cosine squared of theta is equal to 1. And don't forget that if you know this to be true, and we proved this in class, that you can also derive the other two identities. Now, there's a little bit of difference between deriving and proving, but to show you that you don't have to memorize the other two, that you can derive them, reminding you that you can take this statement, which is already true, and you can divide everything by the sine squared of theta on every term. And we see that the sine squared of theta divided, you're allowed to do this with an equation, you can divide everything by the same thing, that the sine squared of theta divided by the sine squared of theta is equal to 1, and the cosine squared of theta divided by the sine squared of theta. And notice we just proved that the cosine of theta over the sine of theta is equal to the cotangent of theta. So what do we recognize here? When we have sine over cosine, that's going to be what? Tangent. If I have cosine over sine, that's going to be cotangent. So in this case, cosine squared over sine squared is, we can think of this as cosine squared theta over the sine squared of theta is the same thing as the cosine of theta over the sine of theta times the cosine of theta over the sine of theta. And so are we not looking at the cotangent of theta times the cotangent of theta? Notice right here, cosine over sine is cotangent. So can we write this as the cotangent squared of theta and 1 over sine squared of theta? Notice that 1 over sine is cosecant. So if I look at 1 over the sine squared of theta, can't this be written as 1 over the sine of theta times 1 over the sine of theta? And so we're looking at nothing more than this is the same thing as cosecant times cosecant. Okay, so we end up with cosecant squared of theta. And there is our second identity. Notice, we can take this equation that's true. We, again, can prove this to be true. And we can derive another equation by dividing everything in the equation by the cosine squared of theta. Okay? I mean, you could technically divide by anything you want, but if we divide by cosine squared, then that works because it's going to cause this to be 1. And there's really infinitely many forms you could derive here, but we want forms that are useful. So if you divide by cosine squared of theta, you're going to get a form that's commonly used. Notice that sine squared of theta over the cosine squared of theta, remember sine over cosine is tangent, we can write this as the tangent squared of theta. And cosine squared over cosine squared is equal to 1. And 1 over cosine squared, remember that 1 over cosine is secant, is going to be secant squared of theta. Okay? So this is just stuff that you're going to use. Everything on the left side of the board are things that you need to just know in order to prove other identities on your homework. So the identities we're going to deal with on the homework are going to be different from what's on the board, but what's on the board here is going to be used every time. And again, you don't have to memorize this stuff, you can derive it. All right, so let's start with, try to keep this quick and to the point, but let's start with the first proof here. Notice we want to go either from left to right or from right to left. Now, I told you guys it's going to help you if you start with the most complicated side of the equation. Okay, notice there's a left side and a right side. If I ask which one's more complicated, I hope you would say the left side. So we're going to start by literally just writing that part of the equation. So we're going to have tangent of theta times the cosecant of theta. And we're going to manipulate the form of this until somehow we can eventually arrive at the secant of theta. Okay? Now, there's a big hint with these proofs. And I'm going to erase this off the board. Okay? Real quick. And in the next lesson, I'm just going to say we know that the tangent of theta is equal to the sine of theta over the cosine of theta. And we know that the cotangent of theta is equal to the cosine of theta over the sine of theta. My hint to make these problems easy as we start is to focus on these two identities. Okay? Meaning that what are these identities going to allow you to do? They're going to allow you to convert any tangent function to sine and cosine, and they will also allow you to convert any cotangent function to cosine and sine. So I tell students this, the easiest way to start for most students is whenever you see a problem is to convert everything into sines and cosines. If you convert everything into sine and cosine, generally you can see the relationships a little more easily. So what we're going to do is notice we have tangent of theta here, so we're going to convert that to a sine cosine form. Notice that the tangent of theta is sine over cosine. So we're going to write this as sine of theta over the cosine of theta. And what do we have here? We have cosecant of theta, and notice we know that the cosecant of theta is 1 divided by the sine of theta. So we have 1 over the sine of theta. And notice we've taken an expression that does not have any sine or cosine functions in it and rewritten it as a function of sines and cosines. And now we can see a relationship here. Remember when we multiply fractions, we can cancel, and so we have sine of theta, numerators cancel with denominators, canceling with sine of theta, and notice now we're left with 1 over the cosine of theta. And if you recognize this, don't lose sight of where you're trying to go. You're trying to go to secant of theta, so we're not done until we arrive at this point. Notice that 1 over cosine of theta is defined as secant of theta. So now we can say that 1 over cosine is equal to what? The secant of theta. And notice that we have now proven that the left side of this equation is equal to the right side of the equation using algebraic manipulation and trigonometric definitions. Okay? Now, the bottom one, notice at the top problem we have multiplication, and on the bottom problem we have addition. So I'm trying to start with the most basic two things that you guys are going to have to deal with here. Multiplication and addition, and how do you handle them? With multiplication, things cancel out. With addition, things do not cancel. We have to use a different technique. Now again, the most complicated side, if you have addition in the problem, I would definitely consider the addition to be more complicated than the multiplication. So why don't we start with the addition? We're going to write the left side of this equation, the tangent of x. Notice that we're using x for the angle instead of theta. It does not matter which variable you use, but you just have to use the same variable throughout the problem. So we have the tangent of x plus what? The cotangent of x. And I told you guys the hint is to convert these functions into sines and cosines. So if we have tangent of x, we want to convert that to sine over cosine. So what we're going to have here is tangent of x is going to be what? the sine of x over the cosine of x. And we have added to that the cotangent of x. Converting that into a sine cosine form is going to be the cosine of x over the sine of x. Now, remember that when we add fractions, we have to have a common denominator. So let me give you just a reminder example. If I'm trying to add 1/2 plus 1/3, we have to get the denominators to match. So we're going to multiply this by 3 over 3. Remember that 3 over 3 is nothing more than 1. So you're multiplying 1/2 by 1. We end up with 3 over 6. And we're going to multiply the 1/3 by 2 over 2. And we end up with 2 over what? 6. This is probably the hardest step for students to get used to, is to getting that common denominator. It's going to be very common. It's going to be very often used in these problems. Notice that we asked, what would I have to multiply the 2 by? If we go back to the beginning, 1/2 plus 1/3, what would I have to multiply the 2 by? And what would I have to multiply the 3 by to get these to match? Well, I can multiply the 2 times 3, and I can multiply the 3 times 2. Okay? So if ever in doubt, just multiply by the other denominator. And if I do that to the bottom, I have to do that to the top. Why? Because when I do 3 times 1, I get 3. 3 times 2, I get 6. Notice that 3/6 is the same thing as 1/2. We're not changing the problem because we're multiplying by 1. 1/2 times 1 is still 1/2. If I multiply the bottom by 2, I have to multiply the top by 2. So this gives us 2/6. And notice that 2/6 is still 1/3. So you're still looking at the same question of 1/2 plus 1/3. And then when you finally add these together, the matching denominator does not change. The 6 stays the same when you add the top. 3/6 plus 2/6 is equal to 5/6. So going down to here, notice that our denominators do not match and we have addition. So we have to get these denominators to match. How? Well, if you're not sure, then just start with multiplying. Let me give some more space. So I'm going to write sine of x over the cosine of x plus the cosine of x over the sine of x. If you're not sure, then start by just multiplying by the other denominators. So we're going to take the cosine of x denominator. Remember that we're focusing on the bottom. We are not worried about the top. If I take the cosine of x denominator and I multiply it by sine of x, and I take the sine of x denominator and I multiply it by cosine of x, notice that these denominators will now have the same thing in them. Both of them will have a sine and a cosine. Now remember, if you multiply by the bottom by sine of x, you multiply the top by the same thing. And if you multiply the bottom by cosine of x, you have to multiply the top by the same thing. And now we're going to multiply these two fractions together. And what does that give us? Well, sine of x times sine of x is sine squared of x over sine x cosine x. That's the first fraction. Now the second fraction, we have cosine of x times cosine of x is going to be cosine squared of x over sine of x cosine of x. Notice now we have a matching denominator. When we add this together, the matching denominator will not change. So what we're going to now have, I'm running out of space, this is going to equal, we're going to add the top. This is going to be the sine squared of x plus the cosine squared of x over the sine of x times the cosine of x. And if you look at this for a moment, you need to quickly recognize whenever you see sine squared or cosine squared on your paper, you're going to be looking at this Pythagorean identity right here. And what does it say? It says that the sine squared of an angle plus the cosine squared of an angle is equal to 1. Now, we see that here, that the sine squared of x plus the cosine squared of x, so we know that that is equal to 1 over the sine of x times the cosine of x. And because now I've created a fraction that has multiplication in it, I can split the fraction apart and write this as 1 over the sine of x times 1 over the cosine of x. And notice where we're trying to go. We're trying to go from addition to multiplication. Notice that we're trying to get to the secant of x times the cosecant of x. And I'll talk to you guys about other techniques in the next video that are going to help you. In this video, my main concern is not necessarily your ability to prove the entire statement as much as it is for you guys to know how to handle multiplication and addition. I need you guys to be able to find a common denominator and also know that multiplication you can cancel. Also practice converting tangent and cotangent into sine and cosine forms. Now at the end here, notice that we have 1 over sine of x. 1 over sine of x is the cosecant of x, and 1 over the cosine of x is the secant of x. And notice, we have now proven that the first part is equal to, or the left side of the equation is equal to the right side of the equation. Notice that the left side of the equation, we manipulated its form until we eventually arrived where? At the right side of the equation. Cosecant of x times the secant of x is the same thing as the secant of x times the cosecant of x because of commutativity of multiplication. We know that 3 times 5 is the same as 5 times 3. So we can assume that to be true. All right, guys, have a wonderful day, and I'll see you in the next video.